Consequently, the thermal boundary layer is much thicker for liquid metals. For these liquid metals, the thermal boundary layer is much thicker for that, and much thinner for oils relative to the velocity boundary layer. So the Pareto number can show how fast the momentum diffuses and how fast the heat diffuses. You can compare these two by Pareto numbers. So you know the relative thickness of the velocity and the thermal boundary layers can be described by PR, and you can know the thermal boundary layer is much thicker for liquid metals and much thinner for oils compared to the velocity boundary layer. It's an important dimensionless numbers for momentum diffusivity and heat diffusivity, and for velocity boundary layer and the thermal boundary layer. So Pareto is a famous German physicist, and we know Pareto number was named after him. And if you would like to calculate a convection heat transfer problem, you should know the flow is laminar or turbulent or in transition situation. Then look at this example. This example shows the laminar and turbulent flow regimes of a candle mock. You can see here, this is a candle, and if there is the candle smoke, this part is the laminar flow, and this part is turbulent. You can see the fluctuation here for the smoke. So what is laminar flow is smooth, streamlines, and highly ordered motion. And what is turbulent flow? The velocity fluctuations and the highly disordered motion. You can see highly disordered. And in between of that is the flow fluctuates between laminar and turbulent flows is the transition part. Most flows encountered in practice are turbulent. And this is another example for laminar and turbulent flow. This one, the behavior of colored fluid injected into the flow in laminar flows, and this is turbulent flows in a pipe. That's the other example for laminar. Layer by layer, the flow layer by layer, and turbulent flow fluctuation. And here, how to divide the laminar flow and turbulent flow. Usually we use a dimensionless number, Reynolds number. This is what is Reynolds number. Reynolds number's physical meaning is about the ratio of inertial forces and viscous forces. How big the inertial forces and how big the viscous forces, that is the ratio of that. It's Reynolds number. So the transition from laminar to turbulent flow depends on different parameters, include geometry, surface roughness, flow velocity, surface temperature, and type of fluid. And this we can show them, we can combine all of them to Reynolds number. At large Reynolds numbers, if the Reynolds number is big, at large Reynolds numbers, the inertial forces, which are proportional to the fluid density and the square of the fluid velocity, are large. You can see this on the black you can see the inertial forces proportional to the rho and the velocity square and L square, and divided by the viscous forces proportional to mu viscosity, this velocity and the length, and divide. You can delete V, delete L, then you left VL divided by mu. You show this. After that, you show this is like this. That this mu equals to mu divided by rho. So Reynolds number. This is the definition of Reynolds number, equals to density rho multiply velocity v and a characteristic length. This is diameter, and divided by viscosity mu. This is the Reynolds number definition. At a small or moderate Reynolds number, the viscous force, this force, are large enough to suppress this fluctuation and to keep the fluid in line. That is laminar flow. And if the Reynolds number is big, is large, then the inertial forces, just now we show these inertial forces, are large relative to the viscous forces, and thus the viscous forces cannot prevent the random and rapid fluctuations of the fluid that is turbulent flow. So there is one critical Reynolds number. That means the Reynolds number at which the flow becomes turbulent. The value of the critical Reynolds number is different for different geometries and flow conditions. The Reynolds number can be viewed as the ratio of inertial forces to viscous forces acting on a fluid element. This is the important dimensionless number for flow, Reynolds number. And you know Reynolds is a famous English engineer and physicist, and with the Reynolds number named after him. This is the great scientist Reynolds. So after that, you know heat and momentum transfer. Heat and momentum transfer in turbulent flow is important because most flows in quantity engineering are turbulent, and thus it's important to understand how turbulence affects wall shear stress and heat transfer. However, turbulent flow is a complex mechanism. Turbulent flow is complex, and it is dominated by fluctuations, and the theory of turbulent flow is still not fully understood. You know, turbulence is very complex and is not fully understood until now. Therefore, we must rely on experiments and empirical or semi-empirical correlations developed for various situations. Turbulent flow is characterized by disordered and rapid fluctuations of swirling regions of fluid. We named that as eddies throughout the flow. You can see this figure, this example. The intense mixing in turbulent flow brings the fluid particle. The 2, 5, 7, 12 is the two different layers fluid particles at different temperatures. They contact to each other and thus enhance the heat transfer. You can see before turbulence, the particles line in different layer, and after turbulence, the different layer particles, they go to other random place, so they contact to each other and change the heat and can enhance the heat transfer. So this, IDs. IDs is important in turbulent flow because, the IDs like this, swirling IDs, they can transport mass, momentum, and energy to other regions of flow much more rapidly than molecular diffusion. The molecule diffuse not very strongly, but the swirling eddies can transfer mass, momentum, and energy to other regions like this turbulent flow. The particles will contact to each other very strongly, and they can change the heat, and temperature can be and to the similar temperature very fast. Turbulent flow is associated with much higher values of friction, heat transfer, and mass transfer coefficient. So turbulent flow is very important for convective heat transfer. Only diffusion is not enough to enhance the heat transfer. So we will analyze the eddies in turbulent flow to see how fast the momentum transfer and how fast the heat transfer. And to calculate the heat transfer, turbulent flow heat transfer, convective heat transfer, and we will use the velocity, pressure, and temperature. We analyze the value of velocity and the value of pressure, and we analyze the temperature distribution. And there is a fluctuating component for velocity. So the velocity can show as average velocity, and the fluctuating component velocity. This is the local velocity. And similarly, the pressure can show similar form, and temperature can be shown as the similar form, average temperature, fluctuating temperature, and this is the local temperature. And in our calculation, we named a turbulent shear stress like this. This is the turbulent shear stress. This density rho and the fluctuating component U and V. This is the time average of the product of fluctuating velocity component U and V. And look at this figure. This figure shows this the average U velocity, and this is the fluctuation of the velocity. So just now we said in the turbulent flow there are eddies. There are swirling eddies to enhance the heat transfer. And here we called the viscosity in turbulent flow mu T as turbulent viscosity, or eddy viscosity. And we called the K T is in turbulent flow the conduction heat transfer coefficient. We called it turbulent thermal conductivity or eddy thermal conductivity. So it's different from the mu of the fluid from the thermal conductivity of the material. So the mu and the K of the mu T and alpha T is different parameters, not the material physical properties. Mu and alpha, or mu and K, the viscosity and the thermal conductivity, are the fluid are fluid properties, and their values can be found listed in fluid handbooks. But this, if you have a t named turbulent, the mu t or alpha t or mu t and kt, that means in turbulent flow, in turbulent convection heat transfer, the viscosity and thermoconductivity in turbulent flow, they are not fluid properties, and their values depends on flow conditions. And the added diffusivity mu t and alpha t decrease towards the wall, becoming to 0 at the wall. Their values range from 0 at the wall to several thousands times the values of molecular diffusivities in the core region. So you know the mu t and kt are not the fluid property. This depends on the flow condition. And after we know the basic conception for convective heat transfer, we would like to solve a problem. We would like to solve the different problems in engineering or in your research topic. So we need to know how many equations we should list to solve the problem. Look at this example. This is the derivation of differential convection equation. Look at this one, this figure. This is a volume, a control volume. And this control volume comes from here. Here is a very small control volume this is a plate, and this the fluid flows across the plate, along the plate, and there is the velocity boundary layer, this velocity boundary layer, and we get a small part. This is the control volume, and the length is dx, and the height is dy. So that is the control volume used in the derivation of mass balance in velocity boundary layer in two-dimensional flow over a surface. This is the list. And in this section, we derive the governing equations of the fluid flow in the boundary layer. And we would like to assume the flow to be steady. Steady flow is easy, and the flow is two-dimensional, and the fluid to be Newtonian with constant properties. Constant properties, constant density, constant viscosity, constant thermoconductivity. That's to make the problem easy, because we consider steady problem, two-dimensional problem, and we assume the constant properties, constant density, constant viscosity, constant thermoconductivity. And we consider the parallel flow of a fluid over a surface, and we take the flow direction along the surface to be x, this x, and this direction normal to the surface to be y, and we choose a differential volume element, the small element here, dx, dy, and we note the fluid flow the surface with a uniform free stream velocity v. But the velocity within the boundary layer is two-dimensional, will change, the velocity will change. And this is v. This along the x direction, we named the velocity is u. And from here, this part, the left part for the volume, control volume, the velocity is u for the fluid. And this part, the velocity change. So the velocity comes to u plus partial u divided by partial x multiply dx. And similar in the y direction, v and partial v divided by partial y and multiply dy. And this is you should first list when you would like to calculate the equations. Now we will apply 3 fundamental laws to this fluid element. We will apply conservation of mass, conservation of momentum, and conservation of energy to obtain the continuity, momentum, and energy balance equations for laminar flow in boundary layer. And to apply the conservation of mass principle is very simple. The rate of mass flow into the control volume equals to the rate of mass flow out of the control volume. That means this is the outlet, this is the inlet, this is the outlet. Then the mass flow into the control volume equals to the mass flow out of the control volume. So the rate of mass flow into the control volume equals to the rate of mass flow out of the control volume. Then you list that this is the rate of this is the rate at which the fluid leaves the control volume from the right surface, this part. And this is the control volume into the control volume. From the left surface is rho u dy multiply 1. And this is the control volume. The fluid leaves the control volume from the right surface, in and out. Then the flow into and the flow out of that. Then we list that. And we're repeating this for the y direction. For the y direction, the fluid flow into the control volume and the fluid flow out of the control volume. And they together, we put these two together, two directions. The fluid flow into the control volume from x direction and from y direction together equals to this equals to the flow out of the control volume, these two parts. The sum of that, the sum of this. Then this is the rate of mass flow into the control volume equals the rate of mass flow out of the control volume. And we simplify that equation and divide it by dx dy and gives the final form. It's very simple. This is the conservation of mass relation in differential form, which is also known as the continuity equation of mass balance for steady two-dimensional flow of a fluid with constant density. So look at this very simple form for mass balance or mass continuity equation. This is a very simple equation for steady two-dimensional flow of a fluid with constant density. And this is the continuity equation or the mass balance equation. And for the momentum equations, is okay. Thank you, Darwin. Thank you. This one, yeah, thank you. This one is the mass balance equation. I just repeat because the black screen just now. We will use this control volume. The mass flow into the control volume equals to the mass flow out of the control volume. And from this direction and this direction. And the rate of mass flow into the control volume equals to the rate of mass flow out of the control volume. For any difficult, complex equations, you can just to use this control volume, and you write the velocity this equation, and the velocity this equation, and the length of this control volume, the length dx, and this the length dy, and after you change from the fluid flow from this left right to the right part, and the velocity change like this, and this is the velocity change from v to v plus partial u v partial y dy, and you calculate the mass balance is using the rate of mass flow into the control volume equals to the rate of mass flow out of the control volume. Finally, you get these simple equations. That's the mass balance equation for steady two-dimensional flow of a fluid with constant density. It's a very simple equation. And for momentum equation, that's similar to that. And what equation you should, what law you should use to get this momentum equation? We use the Newton's second law of motion for the control volume. That is m multiply a equals to f. And what is m? M named m means mass, and a means acceleration in a specified direction. And what is F? F is the net force, including body force and surface force, acting in that direction. So you list the equation. Ma equals to F surface and F body. This is the third M, and this is acceleration, and this is the force. The sum of force of surface and body force. And you list that. You list every part in that. And finally, you get a simple equation like this. That's U. This rho is density. U is the x direction velocity, and V is the y direction velocity, and mu is the viscosity, and P is pressure, X is x direction, and y direction xy coordinates. This is the relation for the momentum balance in the x direction, and is known as the x momentum equation. So finally you get a simple form for momentum balance. And after that, we will get the energy equation. This similar. That is for this steady flow process, the energy into the volume equation, control volume equals to the energy out of the control volume. So you know that the energy can be transferred by work, by heat, by mass. So you can list this equation, and you put every equation for each part into that. You see this, look at this figure. The energy by heat into the control volume in y direction, the mass into the control volume. This is the heat out of that, the mass out of that. And this direction, the heat into the control volume in x direction, the heat into the control volume in x direction. This is the heat out of that, the mass out of that. So finally, you get a simple energy equation. The conservation of energy equation is like this. That rho is density, Cp the specific heat, and U velocity, T temperature, K thermal conductivity. This is the energy conversion equation. So the energy conservation is listed like this. And if we simplify that for a special case, for the special case of a stationary fluid, when the velocity is zero, stationary fluid, the velocity in x direction, in y direction equals to zero. The energy equation reduces, and the steady two-dimensional heat conduction equation is like this. This is the steady two-dimensional heat conduction equation. It's very simple, like this. So these three equations are the mass balance equation. This is the momentum equation. This is the energy conservation equation. So finally, you can use these three equations to solve problem. For example, this is the boundary conditions for flow over a flat plate, and we consider this as a laminar flow and on a flat plate in this figure. And the surface that are slightly contoured, such as, for example, this may be a turbine blade, similar as a small part is a flat plate. And this is x coordinate, and this is y coordinate. And this on the wall, the velocity is zero. On the wall, no slip condition, the velocity uv is zero, and the surface temperature is Ts. And on the velocity boundary layer part, this is velocity v and T infinite. So we list three conservation equations to solve the problem. That is for the mass balance, that is for the momentum balance, that is for energy balance. And you should know the boundary condition. The boundary condition is like this. It's like this. When x equals to 0, this. And the velocity is v, the t is t infinite. X, and when the y is 0, this part y is 0, this y is 0, and this is the uv and the temperature T. And if the y equals to infinite, far from the plate, and the u equals to b, and the temperature equals to T infinite, this is the how to solve this problem. You list the equations and you list the boundary conditions. So after that, you should get the solution of the differential equations after that. And in the problem solution, sometimes you may use this non-dimensionalized convection equations, and you may use the similarity method. Then how to use this method? Then we assume all lines by a characteristic lines L. Then if there is a characteristic lines L, then x divided by L, then you get this x is the dimensionless x, and the all velocities by a reference velocity v, then you get the dimensionless u divided by this reference velocity, and the pressure u divided by rho v form, then this you get a dimensionless pressure. And if you like to use a suitable pressure, suitable temperature difference, For example, T infinite minus T surface for the plate. Then you get a dimensionless temperature. Then you can simplify the equations. And in the equations, you get many dimensionless numbers. For example, Reynolds number, Pareto number, and the boundary conditions is very simple compared to what we get just now. The equations is very simple, and the boundary condition is very simple. And you get several dimensionless number, include Reynolds number, Pareto number in the equations. That is an important method when you solve some problem. And you can see this is a example for that. For two geometrically similar bodies have the same value of friction coefficient as the same Reynolds number. You can see this similar. L, and V velocity, and the Reynolds number is equal. Then the friction coefficient is equal. And for just now, we use some characteristic lines, reference velocity, pressure, and the suitable temperature difference to make the non-dimensional parameters. And you can see parameters before non-dimensionalizing is L, V, T infinite, T surface, V, mu, alpha, and the parameters after non-dimensionalizing is only your left RE, Reynolds number, PR, Pareto number. So you can see the number of parameters is reduced greatly by non-dimensionalizing the convection equations. That is why we introduce this method, because if you use this method, the parameters reduce a lot. 1, 2, 3, 4, 5, 6. And here, only 2 parameters left, Reynolds number, Pareto number. This is a method to simplify the equations. This is what we introduced. When you solve a problem, you can use this non-dimensionalized method to make the parameters reduce greatly. And if we solve the problem of heat transfer, we can use another method, analogous between momentum and heat transfer. This can be used when we learn mass transfer. When you learn mass transfer, you can use the heat transfer equations to get mass transfer equations. And when you study heat transfer problem, you can use some momentum transfer equations or concept or method to get your own solution. And for when you study the convection equations, you have some important results from that. This is you can refer to give a reference for you when you to calculate some problem. You can check if you can use it or not. That's some important results from convection equations. This is what we talked for convective heat transfer, and we introduced the physical mechanism of convection. And one important dimensionless number is Nusselt number, and we tell you how to classify the fluid flow. and we introduced the velocity boundary layer and the thermal boundary layer and the laminar and turbulent flows. And you can use Reynolds number to distinguish the flow is laminar or turbulent flow. And you can use the Pareto number to know the momentum boundary layer, velocity boundary layer, and thermal boundary layer. And you know the heat and the momentum transfer in turbulent flow. The heat and the momentum transfer can be enhanced by eddies in turbulent flow. And just now we introduced the different conservation equations: mass balance, momentum balance, and energy conservation. That's 3 basic equations for you to solve the convective heat transfer problem. And you have some method to use for convection equations to solve the equations. One is non-dimensionalized method, and the other one is similarity method. And you know there are analogies between momentum and heat transfer. And similarly, when we study mass transfer, there are analogy methods for momentum transfer, heat transfer, and mass transfer. This is we introduced in the convection heat transfer part. And first, we have a break, and after that, we will tell you how to do an oral presentation, how to select a topic for your presentation. After we will introduce how to do an oral presentation. Yeah, because next Monday, there are 4 to 5. I think maybe the students in School of Energy Science and Engineering, there are 4 students. And because you are familiar with heat transfer and your research topic are all related to heat transfer. The 4 students in School of Energy Science and Engineering will do the oral presentation on Monday, next Monday. And if you have some questions, you can ask me in the WeChat group. And if you need help for your slides, it's okay for me or Dr. Tang to help you. Only 1 oral presentations in my class for each student. The 4 students, when you finish the oral presentation here, then you don't need to do the oral presentation next time. Next time, the 1, 2, 3, 4, 5 students from mechanical engineering school will do the oral presentation next time. So on next Monday, 4 students from School of Energy Science and Engineering will do the oral presentation related to your research topic. After several minutes, Dr. Tang will give an example for that. You can look at how to do the oral presentations for a research topic related to heat transfer. So have a break. Yeah, have a break first. To organize the oral presentations, structures, and how to name the titles, how to do every slide, and she will explain that slide by slide, page by page. And please, Dr. Tang.
Okay. Hello everyone. And today I'd like to share with you some details about doing the PPT, and I will introduce my project about my PhD students about my PhD degree. And so the first page is about the if you do you can. Sorry. Okay, here. Uh, okay. Here is my presentation I want to share today. The subject is about DEM simulation on flow and heat mass transfer performance of drying process in flow-set baths. For the drying process, it's related with flow, and heat mass transfer is also related with our course. For the first page, we can learn that you should write down the title of your presentation, your name, and oral presentation on a conference. You can write down the conference name at the bottom of the page. For this presentation, so I write down the heat mass transfer 2021. So For the next page, I show the contents of the presentation. If you give a presentation, it generally consists of 4 parts. The first part is background, and the second part is the models. The third part is results and discussion, and the final part is conclusion. For the first part, you could introduce the background of your investigation. You can introduce why you do this project and the aim you want to obtain from the investigation. And for the second part is also a very important part for this presentation. If you do some simulation, for the second part, you should introduce the mathematical models in details and tell the listeners the models you choose and why you choose these models. If you do some experiment, you should introduce the experimental device and the experimental device and the experimental measurement you use in this work. The second part, it depends the method you use. The third part is the results and discussion. For this part is very important because you should show your results and tell listeners what you get from the research. And you should analyze the results by theoretical analysis and by some other method to investigate to learn some details from the research. The final part is conclusion. You can give a brief summary of this presentation. The second page, we show the contents of the oral presentation. We can have a look at this page. The contents we write down at the top of the page. This is title, and the 4 parts name we put the middle in the page. So if you do the PPT, you should arrange the page clearly. Okay, the first part I will introduce the background of my investigation. Before I introduce the background, we can have a look about the layout of the page. We can have a look at the top of the page. I write down the background at the top of the page, and here the subtitle particle system. Because for the background, I will introduce a different section about the background. So I should tell the listeners this part I will introduce. So I write down the subtitle. For the first page, I write down the particle system because this subject is I want to introduce for this page. So here, particle system is a very common phenomenon in nature and involving industrial and production, energy utilizes, and other fields. For the most time, the liquid is could not be neglected, and the presence and cohesive liquid has an obvious effect on particle flow behaviors. We can have a look of this picture. For a dry particle system, particles could be fluidized, and with some liquid introduced, we could find that the flow regime changed, and there's an obvious gas channel here. With the liquid removed, we could find that the particle system transferred from the wet particle system to the dry particle system. Uh, so, so we have to. It's very important to to investigate the effect of liquid present on the particle systems. For this page, I will introduce why I'm going to investigate the wet particle system. Because wet particle system is very common in pollution control, handling wet materials, and transport water limitation problems. For this page, we can have a look at the layout of this page. I suggest everyone to match the figures and the text reasonably, and you can tell the listeners what you want to introduce clearly. It's not suggested to write down the text all the page or show the figures all the page. So you can match the figures and text by some colors and some layout. So that's why I introduced the wet particle system, because the flow and heat mass transfer of wet particle system is a key problem in industrial application. The next page, I will introduce the method I will use in this work. For this work, I investigate the flow and heat mass transfer behaviors by the simulation. For the simulation method, the advantages are saving results, easy operation, and we can capture particle maker movement characteristics. For the simulation method, there are four major methods, including discrete bubble model, true fluid model, and discrete particle model, and lattice Boltzmann model. For this work, I choose the third method, discrete element method, because particles could be treated as a discrete phase, and the movements of particles are tracked, particularly because I want to investigate the effect of cohesive liquid. So the DM is very convenient for adding the liquid bridge force module. So here are some figures and some results from others reference by the DEM. So next part, I will introduce the mathematical models. So for this page, I want to tell you, if you introduce which part, you could highlight it. For example, I will introduce the models, so I will highlight the models. So for the mathematical models, it consists of three parts, including gas phase, solid phase, and exchange between the gas and solid phase between the gas phase and solid phase. So expect that we also consider flow, heat transfer, and mass transfer behaviors at the same time. And for the flow behaviors, for the gas phase, we should consider the mass and momentum conservation equations. And for the heat transfer, we should consider the heat conversion equation. And similarly, the mass conservation equation should also should be considered. And for the solid phase, we can have a look here. For the particle motion, it will be solved by the Newton's second law, and it includes translational and rotational movement. For the translational movement, we can find that gravity, drag force, liquid bridge force, and contact force are considered. And for the rotational movement, the tangential force and rolling friction are considered. For the particle heat transfer and liquid mass change, it's also related with our course. Here for the particle heat transfer, we consider the conduction, and water evaporation. For the convection, Professor introduced this last class. So if you remember that. And for the mass change, we just consider the water evaporation on the particle surface. And we also consider the liquid bridge volume change. It also will affect the liquid bridge force. So here's the models I applied and the structure of the model we built. So here are some equations for the gas phase. If there are many equations, you could show the equations briefly and tell the listeners the equation you choose. For example, I will introduce these slides like this. Here is some equations for gas phase, such as mass and momentous conservation equations, and the viscosity pressure tensor, and unit tensor. So next we can introduce and pass to the next page. Here's some model for translational motion and rotational motion equations for the particle movement. Here are some small video for showing the particle movement. Here are some here are some equations about particle translational motion and rotational motion. We introduced before that particle movement will be solved by the Newton's second law, and here is dominated by gradient pressure force and drag force, gravity and contact force, and liquid bridge force. And so for the rotational motion, we should consider the tangential force from contact force and liquid force and the rolling friction. Here's some equation for the solid phase to describe the particle movement. Here's some contact force model and the liquid bridge model and the equations. And for the rolling friction, I can introduce it briefly. When particles collide with another particle or collide with the wall, we allowed a small deformation before the contact point. So we can gauge that a direct contact between a particle and a wall or between particles occurs with overlap occurring. And for the rotational motion, the torque is generated by contact and liquid force in the tangential direction and rolling friction. And we can find that when particles, we can see the video again. We can find that when the distance between the particles or the particle and the wall is less than the critical distance of the liquid bridge, the torque is only generated by the liquid bridge force in tangential direction only. So here's another stage. So the final stage is that there is no collision occurred. So for the translational motion, particles are governed by a drag force and pressure gradient force. So here's a drag force to describe the momentum exchange between the particle phase and the gas phase. This page, I will introduce the heat and mass transfer models I used in this work. We can find that for the left figure, there are three heat transfer pathways we considered, including heat conduction between particles, heat conduction between particles and walls, and heat convection between gas and particles. So here I want to tell you is about heat convection is the natural heat convection, which is introduced by Professor last time. So if for the wet particle system, we should consider the heat conduction between the wall and particles, heat conduction between particles, heat convection between particles and gas, and the water evaporation uh, uh, covered by the particle surface, because water evaporation also will take away some heat from the particles. So here's some the H is a heat transfer coefficient, and HM is a mass transfer coefficient. So for here, heat transfer coefficient is in the range between between 2 and 10. So it's in the stage of natural heat transfer stage. So as far I introduce the background and the models for
Mokaya
this work. Sorry, what happened? Can you see the screen again?
Yes, Professor.
Okay. Okay, I will continue now. So the third part is results and discussion. So I introduced before that this also is very important part for your presentation. You should introduce results and your analyzation results from this work. So I introduce my results from three parts. The first part is model validation, and the second and third part are bubbling fluid bed and the spot fluid bed, because I do some simulation about wet particle drying process in bubbling and spot fluid bed. So if you do the numerical simulation, we generally will apply the model validation. Model validation. The aim of the model validation uh, is to validate your numerical model is right. The method is that to compare the numerical results with the experimental results from other references and all your experimental data. So here I will introduce the model validation about the models I introduced before in the second part. So the left figure is the structure I used, and I also write down the boundary condition for the simulation. If you do the simulation, you should tell the listeners the structure and the mesh size and the boundary condition, because they are very important parameters for the numerical simulation. And the table I introduced the parameters applied in the simulation, including the bed size, particle parameter, gas parameter, and liquid parameter. If you can introduce a parameter in details, your readers of your paper uh, will get more accurate information from your paper. So for the model validation, we compare the cooling period of the hot sphere. And the right video, we can find that 9 hot spheres are placed in a packed bed, and the initial particle temperature and the fluid bed gas are set to 300 Kelvin. And then we can find that the numerical simulation agreed well with the experimental results. So here's the model validation. We can compare. If your numerical simulation results could compare with could agree with your experimental data, it means that it will dominate that your mathematical model is good. So for this figure, the red line is experimental data from other reference, and the black line is the simulation from this work. So here This is a comparison, and the right video is the simulation I make. You can learn the cooling period directly. So next part, I will apply this mathematical model to simulate the flow to investigate the flow, the drying process in bubbling fluid bed and the spot fluid bed. For the bubbling fluid bed, we can find that. Sorry. Yeah. For the bubbling fluid bed, we define a parameter to describe the function. We define a parameter fr to introduce the effect of the cohesive liquid. And the left figure is particle distribution, and the middle figure is the distribution of the parameter fr, and the left figure is the distribution of Reynolds number, Nusselt number, and Shelved number. Here, Reynolds number is Nusselt, and Shelved number also will be used for the heat and mass transfer behaviors. It's very important parameters. So for this figure, we found that the bubble, you can see that the white area, the bubble and the emulsion phase formed in the bubbling fluid bed. And we can find that the bubble sets are uneven in the bubbling fluid bed due to some stable particle agglomeration formed under the effect of liquid bridge force. So next, we introduce the distribution of Fr as a function of the particle volume concentration. So here you can use different analyze method to show your results, include such as a video, a figure, or a table. So here I use the figures to show my results. If you have many figures, you can group these figures into one figure. You can give more results and information to your listeners. So from this figure, we can get that the bubbling fluid bed could be divided into three regions, including bubble, intermediate, and emulsion regions, according to the different particle volume concentration. And with an increase of particle volume fraction, the Fr appeared a decreasing trend. It might be explained that a particle formed of obvious agglomeration and the effect of contact force increased. For the bubble phase, the liquid breath force was obvious because particles with less collision due to the less particle volume fraction. So this page, we also analyze the relationship among the Fr, Reynolds number, Nusselt number, and Shelved number. I can remove the text box. You can see this screen clearly. So we analyze the relationship among these parameters. So you can define different parameters with different colors to show your results directly. So for this page, we show the different heat transfer pathway in the bubbling fluid bed. In the second part, we introduced that we consider the heat conduction between particles, heat convection between particle and gas, and water evaporation. So from figure we can see that for the emulsion phase, this dark color particle conduction occupied a large amount due to the higher particle concentration at upper bed, and near the gas light at the bottom of the bed, particle convection played a more dominant role due to near fluidization gas inlet with higher and more uniform gas temperature and velocity. And for the intermediate phase, for this color, we can find that heat convection play an important role due to more obvious momentum and heat exchange. So for the bubbling fluid bed, we can learn that for the different regions, different heat transfer pathway will play the domain role in different regions. So next part, I will introduce the drying process in a spot fluid bed. Compared with the bubbling fluid bed, the structure is different, and the parameters applied, the parameters for the particle density and particle diameter and gas velocity and are different. So if you give different operation, the fluid regime will change. So this figure is the structure of the spot fluid bed, and here we also show the boundary condition for the simulation. And the left table, we show the parameters applied in this simulation. Also includes the bed size and particle parameter, gas parameter, and liquid parameter. So here's a video of the drying process for the spotted fluid bed. We can find that at the initial stage of drying, we can find there's an obvious gas channel. This phenomenon also could be found and introduced in the first page of our presentation. So, and with the gas fluid particles and with the water evaporation during the drying process, we could find that particles are fluidized gradually, and on this page, we analyze the pressure drop and bed head for the drying process. According to the pressure drop signal, we could divide the drying process into 4 stages. The first stage, we can find that the pressure drop and pattern changed rapidly because there are some obvious agglomeration, which is a resistance for the gas movement. So the pressure drop changed rapidly. And for the stage 2, we found that the fluid gas entered the bed through the gas channel. So for the left figure, here the gas channel formed, so the pressure drop is more uniform. So, and for the third stage, the wet particle system was gradually converted into a dry particle system. So this part, the pressure drop is violent. And the final part, when the particle system is converted to the dry particle system completely, we found that the pressure drop and bed height varied smoothly around a constant value with a specific frequency. So we can get some information by analyzing the figures you got, including the line and the particle distribution from different figures. And here we show the instantaneous liquid content and the particle temperature and the Nussel number and Shoved number in a color map. So from this figure, we can get the information directly, including the height of the different value and the different color for the value, and we can got that in the dilute region for the spot region in the middle of the bed. You can find that there are two peaks in this figure. The momentum, heat, and mass transfer exchange is violent. And in the dense region, especially near the walls, you can find that the momentum, heat, and mass transfer exchange is more smooth. So we can get that as the drying process continued, the particle temperature increased gradually and the bed temperature distribution more uniform. And so finally, we show the distribution of particle velocity as a function of particle volume fraction, and the particle velocity is increased gradually from the sports region. Here, the sports region, and spreading to analyzed region. And at the 30 second, the moment of 30 seconds, the particles were almost completely fluidized, and we can find that the particle velocity peak moved from the 0 to the 0.15, and the particle velocity distribution at the moment of 100 seconds was similar to the 30 second. And this phenomenon demonstrates that white particles were converted into a giant particle system during the third stage, and we can analyze the results. Analyze the results by combining the previous results and figures like this. Here's stage 3. And so here, this page we group 8 figures. So we group 8 figures into one figure. So you can provide more information, and it's more convenient for readers to understand the results you want to provide. So this page we analyze the Nussel number, showed number as a function of the Reynolds number. And for the Reynolds number corresponding to the intersection point of Nussel number and showed number here. And this point increased as the drying process progress. And we found that the mass exchange are more obvious than that of heat exchange before the intersection point was reached. And so here, the third part and is finished. You also found that this part I used to occupy the most time in this of this presentation. So you could introduce the results in details to tell listeners what you get from your results. And so the final part is a conclusion of your research. So we give a brief summary. You can read the conclusion to the listeners. For example, we can find that the drying process can be divided into 4 stages according to the pressure drop, and the particle temperature increased gradually, and the bed temperature distribution became more uniform increase, and the enhancing momentum exchange into including increasing gas velocity and particle diameter, and the decreasing gas viscosity could increase heat and mass transfer capabilities. So here the other presentations, and if you have some question or there are some parts you are not clear, you can tell me and by the WeChat and email. Thank you.
Yeah, so presentation. Do you have any other question about that? About how to do the oral presentation? Then you can see from the screen. Usually, the first part is about the background of your research topic, and after that, you will show the models or the experimental setup, experimental method, and to show the results and discussion, and finally, conclusion part. And when you arrange each slides, then you can see there is a subtitle on that. On top, there is a subtitle. Yes, the subtitle for each part. And you show the results, and you